In late 2025, the United States Department of Energy renewed more than $625 million for 5 national quantum information science research centers, a signal that the federal government sees quantum not as an experiment, but as an emerging industrial base. In parallel, job postings that require quantum skills have multiplied compared with the early 2010s, and elite universities now run dedicated quantum engineering tracks alongside physics and computer science. Even so, employers report more openings than qualified candidates, suggesting the labor market is tight at the very moment. Investment is accelerating. The present push rests on groundwork laid in 2018, when Congress passed the National Quantum Initiative Act to coordinate research and workforce development across agencies and regions. The program formalized a national strategy, linked laboratories with universities and firms, and gave the field a durable policy spine. Subsequent legislation, including the CHIPS and Science Act, expanded funding streams and embedded workforce training into the nation's broader technology agenda. Today's hiring pulse is therefore the visible output of a multi-year policy arc rather than a sudden pivot. Across industry, expectations are sober but sizable. Consulting analyses project that by the mid-2030s, quantum computing could support a global market measured in tens of billions of dollars, with additional value from quantum communications and sensing. By the early 2040s, the combined market for quantum technologies could approach $200 billion, assuming steady progress in error correction, materials, and systems integration. These are not near-term revenue claims. They are decade-scale estimates that align capital formation with long research timelines and slow diffusion into regulated verticals such as finance, chemicals, mobility, and life sciences. The causal mechanism linking research spend to real hiring starts with access. When cloud providers expose early quantum devices through managed services, they move the field from laboratory instruments to software addressable resources. That shift created roles for software engineers, compilers, control electronics specialists, and product managers who can translate use cases into experiments. Large firms such as IBM and hyperscalers that host quantum services normalized this stack, while specialized hardware companies built roadmaps around qubit fidelity and scale. The result is a hybrid market in which classical high-performance computing teams collaborate with quantum groups on narrowly scoped proofs of concept in simulation, optimization, and materials modeling. Policy amplified demand, but supply is constrained. Analyses find that for every 3 quantum job openings, there is roughly 1 suitably trained candidate, implying persistent scarcity without targeted training. The gap is most acute at the intersection of physics and computer science, where employers seek people comfortable with linear algebra, error mitigation, cryogenic systems, and software tooling. Without stronger pipelines, fewer than half of posted roles could be filled in the near term, and firms will continue to hire internationally or rescope positions to adjacent skill sets. This is less a headline shortage than a predictable outcome when a new discipline professionalizes faster than universities can adapt curricula. Credible institutions converge on the same prescription: build a quantum literate workforce that spans technicians, engineers, and domain experts. The Organization for Economic Cooperation and Development highlights skills development as a central policy lever, alongside supply chain resilience and cross-border collaboration. The United States National Quantum Initiative ecosystem and the CHIPS and Science Act emphasize training funds, internships, and regional centers that anchor talent in place. University programs now blend physics with electrical engineering, computer science, and materials, reflecting how hiring managers write actual requisitions. This is what a maturing technology market looks like when public policy is aligned with industrial demand. Forecasts are only meaningful if jobs become durable roles inside firms. Here, sector dynamics matter. Automotive, chemicals, financial services, and pharmaceuticals have structured pipelines of computational problems where quantum methods could, over time, deliver advantage. The early work involves algorithmic research, hybrid solvers, and benchmarking against classical baselines. That mix favors teams that can evaluate value capture rather than chase demonstrations. Hiring therefore, leans toward computational scientists, quant developers, and product analysts who can frame problems, measure gains, and navigate regulatory and data constraints. The center of gravity sits inside research and development and advanced analytics groups, rather than in standalone quantum departments. The human consequences cut along familiar lines in advanced technology adoption. High-skill roles cluster in coastal metros with research universities and national laboratories, while second-order opportunities appear in supplier ecosystems for cryogenics, photonics, vacuum systems, and control electronics. Compensation tracks with adjacent occupations because there is no official quantum category in federal statistics. Positions are classified under physicists, electrical engineers, or computer and information research scientists. Median pay levels in those categories are high by national standards, but they also require graduate education and years of specialization, reinforcing barriers to entry for workers outside elite training pathways. The current risk is narrative drift. Quantum attracts attention, but the labor market is still small compared with artificial intelligence or software broadly. Brookings warns against conflating public fascination with true capacity and notes that public understanding lags, even as Congress moves to reauthorize foundational programs. The policy task is to sustain investment and workforce development through periods when progress is incremental and results are technical. Hype cycles are tolerable in capital markets. They're harmful in education planning, where cohorts cannot pivot every 2 years without eroding depth. Clear communication protects students and firms from misaligned expectations. For workers, the practical distinction is between quantum core and quantum adjacent roles. Quantum core jobs demand deep physics and hardware knowledge. Superconducting or trapped ion device engineering, cryogenics, microwave control, and quantum error correction. Quantum adjacent jobs sit in software, cloud orchestration, verification, cybersecurity, and domain modeling, where familiarity with quantum concepts enables collaboration without requiring experimental expertise. The market currently creates more adjacent roles than core ones, which broadens the funnel for computer scientists and engineers who can learn domain context while contributing immediately to platform and tooling work inside large firms. Education systems are adapting, but the shift will take years. Policy primers emphasize anticipatory governance. Invest in general mathematical and computational fluency, integrate quantum modules into existing engineering degrees, and expand technician training for laboratory operations. The lesson from the artificial intelligence boom is direct. Scalable talent comes from mainstream programs with targeted electives, not from boutique tracks alone. Community colleges and regional universities can anchor technician pipelines, while research universities expand interdisciplinary master's programs that convert strong engineers into quantum literate hires within 2 to 3 semesters. Companies face their own execution problem. The credible approach is to staff small teams that evaluate high-value use cases, build internal literacy, and partner with vendors through cloud platforms. That model avoids stranded investments while preserving option value as hardware improves. Consultancies project that value will accrue unevenly and later than early marketing suggested. Leadership teams should treat quantum as a portfolio of experiments embedded in digital transformation, not as a standalone bet. Boards will ask for measurable outcomes tied to domain metrics rather than qubit counts, encouraging disciplined hiring and fewer vanity roles. On the public side, workforce development is inseparable from regional industrial strategy. Renewed Department of Energy funding signals multi-year continuity for national laboratories that train postdoctoral researchers and host user facilities. State initiatives couple that capacity with local employers, ensuring graduates see viable careers without relocating abroad. International coordination remains essential given the concentration of expertise in a handful of countries. Policy forums stress both open collaboration and security-minded controls, a balance that affects visas, joint labs, and curriculum standards. The outcome will shape where teams form and how mobility patterns evolve over the next decade. The outlook through the mid-2030s is measured. If hardware roadmaps hit fidelity and scale milestones, industry pilots may harden into production workflows in specific niches. If progress is slower, the market will still generate stable demand for researchers, software engineers, and technicians who maintain testbeds, build control stacks, and integrate simulators into classical environments. Either path sustains hiring, but only one delivers step change applications. Policy reports and market studies agree on the main constraint: talent depth. The next phase depends less on headlines and more on whether education systems can produce cohorts fluent in both quantum theory and practical computing. A calm conclusion follows from the evidence. Quantum jobs are real and growing from a small base, anchored by federal programs, cloud access, and steady private investment. The field's credibility rests on disciplined hiring, interoperable tooling, and transparent benchmarking against classical methods. Over the next 10 years, the most resilient workers will be those with strong mathematical foundations, robust software skills, and the patience to specialize without chasing slogans. Institutions that invest in broad STEM capacity and targeted quantum literacy will convert today's research surge into durable employment. Progress will be uneven, but it will be cumulative.